Hello math students. Today's video is lesson 2.2, falling off a log. 2.2 is dealing with graphing logarithmic functions. So for the first three, we're just going to look at basic graphs of log base 2 of x, log base 3 of x, and log base 4 of x. So it says to construct a table of values and a graph for each of the following functions, and be sure to choose at least two values in the interval 0 to 1. So number 1, I want to graph f of x equals log base 2 of x. So I'm going to create a table, and I need to decide some numbers to plug in for x. So because this is log base 2, I'm thinking that powers of 2 would probably be the best type of number to plug in. So maybe if I look at 1/4 and 1/2, then I'm going to go 1, 2, 4, 8, and 16. So we'll see when I plug these numbers into the log, I'm going to get integer answers. So if I were to go and do log base 2 of 1/4, I'm wanting to know what exponent goes on 2 to get a 1/4. Because it's 1 over a number, my answer is negative. And I'm going to ignore that 1 on top. What exponent goes on a 2 to get a 4? 2 to the 2 equals 4. So my answer is going to be negative 2. Similar thing for log base 2 of 1/2. I want to know what exponent goes on a 2 to get a 1/2. It's going to be a negative. Ignore the 1 on top. 2 to the 1 equals 2, so it's a negative 1. Log base 2 of 1. Anytime we have a 1 as the input on our logarithm, the answer is always going to be 0. Because any number with an exponent of 0 is always equal to 1. So then I go on log base 2 of 2. This is asking what exponent goes on a 2 to get a 2. It's going to be a 1. Log base 2 of 4. 2 squared equals 4. Log base 2 of 8. 2 to the 3 is equal to 8. And then log base 2 of 16. 2 to the 4 is equal to 16. So now I have a few points that I can put on my graph. So at 1, at x equals negative 1 or 1/4, my output was negative 2. 1/2 gave me a negative 1. Then a 1, 2, my output was 1, 4, my output was 2, 8, I was at 3, 16, I'm at 4. So then I go and connect the dots. So this is the graph of log base 2 of x. Let's look and see how log base 3 of x compares. So I'm going to create a table of values again, but instead of doing powers of 2, I'm going to look for powers of 3. And I'm going to choose some fractions to be part of my table. So I'm going to look at 1/9 and 1/3, and then I'm going to go 1, 3, 9, and then 27 is power 3, but it's not going to go fit on my graph, so I'm not going to worry about doing that point. So let's look and see what log of each of these numbers is. So log base 2 of 1 over 9, log base 3 of 1 over 9 is equal to negative 2, because 3 to the 2 is 9. Log base 3 of 1 over 3 is going to be negative 1. Log base 3 of 1 is equal to 0, because any number with an exponent of 0 equals 1. log base 3 of 3 is equal to 1, and log base 3 of 9 is equal to 2, because 3 squared equals 9. So let's go ahead and put these on the graph. So I always, so I've got my 1/9 gives me a -2. 1/3 is at -1. I always have an x-intercept at 1. I have 3, 1, 9, 2. And then 27, 3 would be my next point. But I didn't leave room on the graph for that, so I'm just going to make sure that I don't quite reach 3. So this is the graph of log base 3 of x. Log base 4 of x is going to be a similar thing. Except I'm going to look for powers of 4. So I'm going to see what is log base 4 of 1 over 16. It's a -2. What is log base 4 of 1 over 4? It's a -1. What is log base 4 of 1? It's equal to 0. Log base 4 of 4 is equal to 1. And log base 4 of 16 is equal to 2. So let's go put these points on the graph. At 1/16, which is really close to the y-axis, I'm at -2. 1/4, I'm at -1. 1 is at 0. 4 is at 1. 16, all the way over here, is at 2. So go and connect the dots. So that is the graph of log base 4 of x. So we should notice, if I was to go back and look at the other graphs, so log base 4 of x, log base 3 of x, log base 2 of x, these graphs all look really similar. So number 4 is asking us what similarities we see in the graph. One of the first things that I notice is that all 3 graphs have the same vertical asymptote. So if you don't remember what this word means, asymptote, an asymptote is just a line the graph gets really close to. So we could think about this as kind of being a boundary line for my graphs. If I look back at number 3 on the y-axis, you can see my graph is getting really close to the y-axis but never quite reaches. If I look back on number 2, I have the same kind of thing. Also on number 1, the y-axis is my boundary line for the graph. Another thing that I noticed about all 3 graphs is they all have the same basic shape. They're all increasing, but they're increasing fairly slowly. So I'm going to put that as something that they have in common, is that they have the same basic shape and are all increasing. Shape. So they are all increasing. And then finally, I'm going to say that they all have the same x-intercept. Right here, and right here. They all have that same point. So I'm going to say, for my final thing they have in common, they all have the same x-intercept, which is 1, 0. So then the things that are different the graphs are basically the same, except they are all growing at different speeds. So log base 4 of x is growing pretty slow, log base 3 of x grows a little faster, and log base 2 of x grows a little bit faster. So differences I see in the graphs, I'm going to say that they're growing at different rates. And that has to do with the base. So the effect of changing the base on the logarithmic function, that changes the rate at which the graph grows. So as the base increases, you should notice that I'm going to say that the growth rate, or the speed that it is growing, increases or decreases. So this is looking at log base 2 of x, log base 3 of x, and log base 4 of x. So now we're going to look specifically at log base 10 of x. So base 10 is used really commonly in exponential and logarithmic functions. Because of that, we will typically abbreviate log base 10 of x and leave it without the base. So if you ever see a log without a base, that is automatically base 10. So this is the same as that. Because we use this so often, we call this the common log. So base 10 is a common log. We don't write the 10 on the base. So let's go ahead and look at the graph of log of x. So I've already gone and made the graph on Desmos. This is the graph of log x. We should notice that it's growing a lot slower than log 2, log 3, and log 4. So all three of those reached 2 before I got an input of 20. Log of x is going to have to go all the way up to 100 before it even gets 2. So how does the graph compare? I'm just going to say that it just grows a whole lot slower. So once again, the bigger the base on your logarithm gets, the slower your graph is going to grow. So let's look at some different things with these logs. So what do you guys think is going to happen if I add a number in front of a log? So this is similar to secondary math 2 when we looked at things like f of x equals x squared plus 2. This was just a parabola that had been shifted up 2. So my vertex was at 0, 2 instead of 0, 0. So remember, that's the bottom of the parabola. So it'd be something like this. It's been moved up 2. So the same kind of thing is probably going to happen with a log. So I'm going to say my prediction is it's going to move up, but it could also move down, depending on what a is equal to. So let's go ahead and look at some examples of where I've added positive and negative numbers to the log. So the effect of adding a and the effect of subtracting a. So I've gone ahead and I have looked on Desmos to see, well, what happens if I add a number. So I did 1 plus log x. That is this green graph on top. So that's the top graph. And then if I did negative 2 plus log x, that is the graph that is on the bottom. So we should notice that when I add a number, everything moves up the exact same amount. So all of these went up 1. So adding a is going to move your graph up a units. If I subtract a, or that's the same thing as adding negative a, I notice that my graph moves down. It moves down a unit. So on this one I did negative 2 plus log x. So my entire graph moved down 2. So subtracting a is just going to move the graph down a units. Let's see what happens if I add and subtract numbers inside of the parentheses. So this is similar, once again, when we were looking at quadratics. If I was to do something like x minus 2 squared. Subtracting inside of the parentheses moved my vertex to the right. So this right here would make my vertex be at 2, 0. So the graph would be like this, or it's just moved to the right. So I'm thinking the same kind of thing should probably happen with a log. So I'm going to predict that it's going to move my graph left or right. So let's look and see, does that happen? So what would be the effect of adding b? What would be the effect of subtracting b? So I've already gone and I have put on decimals some graphs. So I have log of x plus 1. That is the graph that is on the left. Log of x minus 3. That is the one on the right. So adding moves my graph to the left. B units. And subtracting is going to move my graph to the right. So it's the same thing as when we did quadratics last year. So let's go ahead and look at some examples of writing equations for functions and also, given an equation, sketching a graph. So in number 8 it says write an equation of the function that is a transformation of log base 2 of x. One thing that makes this a lot easier for me is if I can see log base 2 of x in comparison to my transformation. So I'm going to look back on what we did on number 1, and I am going to sketch the graph of log base 2 of x. The way that I do this is I start at 0 and I look at powers of 2. So I've got log base 2 of 1 is 0, log base 2 of 2 is 1, log base 2 of 4 is 2, log base 2 of 8 is 3, log base 2 of 16 is 4. And then I have my vertical asymptote on the y-axis. So I should notice that every single point on this graph has been moved left 3 units. And that includes my vertical asymptote has been moved over 3. So my transformation, I'm just going to go ahead and say everything has been moved right 3. So when I write the equation, if I'm moving, I'm sorry, it's not to the right, it's moved to the left. Let me go and fix that. So I moved everything to the left. 3. And so my function is going to be f of x or y. It doesn't matter whether I use either one of those. Is log base 2 of x plus 3. And that would be my answers because I've moved log base 2 of x left 3 units. Let's look at this next one. Once again, I'm going to start by putting the graph of log 2 of x on the same graph so I can have something to reference. So I start with my x-intercept at 1, regardless of the base. And then I'm going to look at powers of 2. So 2, 4, 8, and 16. And then I'm going to connect those, make sure I keep my vertical asymptote on the y-axis. This one, I should notice, does not have a horizontal shift because my vertical asymptote is still on the y-axis. But I should notice that everything has been moved down 2 units. So my transformation is down 2. So my equation is y equals -2 plus log base 2 of x. And that is my equation for this graph because I have that vertical shift down 2. So now let's look at some where I am going to graph a log given the equation. So I have 2 plus log base 2 of x minus 1. I need to first identify what do the different numbers in my log do. So this 2 right here is going to move my graph up 2. This minus 1 moves my graph to the right 1. So I'm going to start by putting log base 2 of x on here. Look at powers of 2. And connect the dots. So I want to take every single point on this graph and I want to move it up 2 and right 1 and put a new point there. I'm going to take each point, once again, move it up 2 and right 1, up 2, right 1, put points on each of these spots. And I also have my vertical asymptote had to move right 1 unit as well. So I'm going to put a dotted line there just so I know that I can't cross that line. And then I'm going to go and connect. So this blue graph right here is the graph of log base, or 2 plus log base 2 of x minus 1. Let's go ahead and do one more example. So I need to identify what my transformations are. I have this minus 1. Since it's a negative 1 that's added to the log, that moves everything down 1. This plus 2 in the parentheses moves everything left 2. Let's go ahead, look at the graph of log base 2 of x. Once again, I always have an x-intercept at 1, and then I'm going to look at powers of 2. Connect the dots. So I'm going to take every point on this graph. I want to move it down 1, left 2. Down 1, left 2. Down 1, left 2. Down 1, left 2. Down 1 and left 2. I'm also going to take my vertical asymptote. I'm going to move it left 2 as well. So I'm going to have a point at each of these spots. So these down 1, left 2 points. And then I'm just going to go ahead, connect the dots. So this blue graph is the graph of g of x.